Landslide Early Warning System, an integrated approach to mitigating disaster risk. Landslides are among the most destructive natural hazards worldwide, posing significant threats to human lives, infrastructure, and ecosystems. Triggered primarily by rainfall, earthquakes, volcanic activity, and human interventions, landslides cause enormous economic losses and social disruption every year. According to the World Health Organization, WHO, and the United Nations Office for Disaster Risk Reduction, UNDRR, landslides result in thousands of fatalities annually, with developing nations being particularly vulnerable due to poor land management, unplanned settlements, and inadequate monitoring systems. To reduce this risk, the development and deployment of landslide early warning systems, LEWS, have become increasingly critical. Much like flood or cyclone warning systems, LEWS provides timely and reliable information about the probability of landslide occurrence in a particular region. By issuing alerts before disaster strikes, these systems enable authorities, communities, and individuals to take preventive measures, thereby saving lives and reducing economic losses. This video explores the concept of landslide early warning systems, their working principles, technologies involved, challenges, and the way forward in building more resilient societies. Understanding landslides. What is a landslide? A landslide is the movement of rock, soil, or debris down a slope under the influence of gravity. Landslides vary in speed from slow creep to rapid flows that can devastate communities within minutes. They are generally categorized into rockfalls, debris flows, mudslides, and earth slides, depending on the material and movement type. Causes of landslides. 1. Natural causes. Intense or prolonged rainfall, earthquakes and volcanic activity. Slope erosion due to rivers or glaciers. Weathering of rocks. 2. Human-induced causes. Deforestation and slope destabilization. Road construction, mining, and quarrying. Poor drainage systems. Unplanned urbanization on unstable slopes. Impacts of landslides. Human impact. Loss of lives, injuries, and displacement. Economic impact. Damage to houses, roads, railways, pipelines, and agricultural lands. Environmental impact, river damming, habitat destruction, and alteration of natural landscapes. Given the suddenness and destructive potential of landslides, developing early warning mechanisms has become essential for disaster risk reduction. Concept of landslide early warning systems. A landslide early warning system, LEWS, is defined as a set of tools, protocols, and actions that predict the likelihood of a landslide event and disseminate alerts to at-risk populations in advance. The primary objective is to minimize the impact of landslides by enabling timely evacuation and protective actions. The United Nations International Strategy for Disaster Reduction, UNISDR, defines an effective early warning system as consisting of 4 interconnected components. 1. Risk knowledge, understanding landslide hazards, vulnerabilities, and risk levels. 2. Monitoring and forecasting, observing indicators like rainfall, soil moisture, and ground movement. 3. Dissemination and communication, transmitting timely warnings to stakeholders and communities. 4. Response capability, ensuring people know how to act upon receiving a warning. Components and working of landslide early warning systems. 1. Hazard mapping and risk assessment. Hazard mapping is the foundation of a LEWS. Geologists and engineers study slope stability, soil composition, and past landslide records to identify vulnerable areas. Geographic Information Systems (GIS) and remote sensing are widely used to produce landslide susceptibility maps. These maps form the baseline for deploying monitoring instruments. 2. Monitoring technologies. Several indicators signal the onset of a landslide. A robust LEWS employs a combination of monitoring technologies to track these indicators. Rainfall monitoring. Since intense or prolonged rainfall is a key trigger, rain gauges and weather radars measure precipitation levels. Threshold rainfall models are then used to predict potential landslides. Ground movement sensors. Instruments like extensometers, inclinometers, and tiltmeters detect slope deformation. Geotechnical sensors. Piezometers and soil moisture probes measure pore water pressure and soil saturation. Remote sensing and drones. Satellite-based synthetic aperture radar (SA) and aerial drones detect ground displacement over large areas. Seismic monitoring. Useful in landslide-prone regions with frequent earthquakes. 3. Data analysis and forecasting. Collected data are transmitted in real time to centralized servers. Advanced computational models analyze the relationship between rainfall, soil properties, and slope movements. Machine learning algorithms are increasingly being applied to improve prediction accuracy. Forecasting types. Regional scale forecasting provides warnings for broader areas, usually based on rainfall thresholds. Site-specific forecasting focuses on localized slopes with detailed monitoring, giving more precise alerts. 4. Communication and dissemination. The effectiveness of a LEWS depends not only on accurate forecasts but also on how warnings are communicated. Alerts must be clear, simple, and actionable. Delivered through multiple channels: SMS, sirens, radio, mobile apps, and community volunteers. Disseminated with enough lead time for evacuation. 5. Community preparedness and response. Communities are the first responders in any disaster. Regular training, mock drills, and awareness campaigns ensure that people know how to act upon receiving a warning. Community-based early warning systems, where local volunteers operate simple rain gauges and report anomalies, have shown great success in countries like Nepal and India. Examples of landslide early warning systems around the world. 1. Italy Emilia-Romagna Regional System. Italy, one of the most landslide-prone countries in Europe, has developed advanced LEWS using rainfall thresholds, remote sensing, and GIS-based hazard mapping. The Emilia-Romagna region pioneered regional-scale early warning with significant success. 2. Japan Integrated Warning Systems. Japan has one of the most sophisticated systems, combining real-time rainfall data, slope monitoring, and strong communication networks. The government issues color-coded warnings to residents through television, radio, and mobile networks. 3. India Uttarakhand and Kerala initiatives. India's Geological Survey and Indian Space Research Organisation, ISRO, have initiated pilot LEWS projects in Himalayan and Western Ghats regions. In Kerala, rainfall threshold-based early warnings were effectively issued during the 2018 floods. 4. Nepal, community-based systems. Nepal has implemented low-cost, community-driven LEWS, where villagers use simple rain gauges and SMS-based reporting. This grassroots approach has saved lives in remote areas lacking advanced infrastructure. Benefits of landslide early warning systems. 1. Life-saving potential. Timely evacuation reduces casualties. 2. Economic protection. Infrastructure and agriculture losses are minimized. 3. Community empowerment. Increases local resilience and awareness. 4. Scientific advancement encourages innovation in geology, data science, and engineering. 5. Policy and planning supports governments in land use planning and disaster risk reduction. Challenges in implementing LEWS. Despite the proven benefits, several challenges limit the effectiveness of LEWS. Technical challenges. High variability of geological conditions makes prediction complex. Infrastructure limitations. Remote areas lack electricity, internet, and monitoring equipment. Financial constraints. Installation and maintenance of sensors are expensive. Data gaps. Inadequate historical landslide and rainfall data hinder accurate threshold modeling. Community engagement. Lack of awareness or mistrust in warnings can reduce effectiveness. False alarms. Overprediction may cause unnecessary panic and reduce trust in the system. The future of landslide early warning systems. To overcome these challenges, innovations and strategic approaches are required. 1. Integration of artificial intelligence, AI, machine learning models can improve prediction accuracy by analyzing complex datasets. 2. Internet of Things, IoT, low-cost IoT-enabled sensors can transmit real-time data from remote slopes. 3. Satellite technology. Continuous monitoring using satellites provides wide coverage at relatively low cost. 4. Crowdsourcing and citizen science. Communities can act as data collectors through mobile apps, reporting rainfall, cracks, or unusual slope movements. 5. Policy frameworks. Governments must integrate LEWS into national disaster management strategies with clear guidelines for funding and coordination. 6. International collaboration. Landslides often occur in transboundary regions. Regional cooperation and data sharing enhance preparedness. 7. Climate change adaptation. With increasing rainfall variability due to climate change, LEWS should incorporate climate models for better long-term planning. Case study: Kerala landslides, 2018. In August 2018, Kerala, India, experienced one of its worst floods in a century, triggering numerous landslides in the Western Ghats. Hundreds of people lost their lives, and thousands were displaced. However, in some regions where threshold-based rainfall warnings were issued, communities evacuated early, significantly reducing casualties. This demonstrated that even simple rainfall-based LEWS can be life-saving when combined with community preparedness. Conclusion: landslides are a growing threat in many parts of the world, intensified by climate change, deforestation, and rapid urbanization. While prevention of landslides is often impossible, early warning systems provide a practical and effective solution to reduce risks. By combining hazard mapping, modern monitoring technologies, effective communication, and community participation, landslide early warning systems can transform vulnerable regions into resilient societies. Investments in technology, data collection, and public awareness are essential. Governments, scientists, and communities must collaborate to ensure that warnings are not only issued but also understood and acted upon. As the world faces increasingly frequent and severe disasters, landslide early warning systems stand as a vital pillar of disaster risk reduction and sustainable development.